Okay, this is a third of the videos, or depending on how you're watching them, perhaps a second. But this is going to cover numbers 66, 68, and 69. It's not going to cover number 67 nor 70 because 67 and 70, they deal with diffusion and effusion and equations that deal with that, and I didn't feel the need to cover that, so obviously you won't be test on it. So we're going to skip 67 and 70. It won't be on your test, but we will be covering 66, 68, and 69. 66 and 68 deal with STP. Okay, 68 is going to call upon very important piece of information you're going to need to know about all gases at STP. And then 69 is going to introduce us to our ideal gas law, okay? But let's tackle number 66 first. And number 66 talks firstly, let's read it. It says that at a deep sea station that is 100 meters below the surface of the Pacific Ocean, workers live in a highly pressurized environment. How many liters of gas at STP must be compressed on the surface to fill the underwater environment with 2.00 times 10 to the 7th liters of gas at 20 atmospheres? Assume that the temperature remains constant. Okay. Part of any good problem solving is knowing what is important and knowing what is superfluous or extra and therefore unnecessary. Because we have dealt with nothing in this chapter about distance as in meters, this is going to be useless. Okay? Nobody cares. At a deep sea station, comma, workers live in a highly pressurized environment. That's all we really need to know. This little piece of information that says 200 meters below the surface of the Pacific Ocean, it looks important. I mean, it looks official. It's got 200, and there's a dot followed by a unit. It's not a naked number. It's probably significant. And sometimes problems throw information like this in, superfluous, just to throw you off a little bit. But one of the keys to this problem is going, wait a minute, this whole chapter, I didn't have one problem or one concept that really dealt with distance as measured in meters. So I'm telling you right now, it's superfluous. On a test, that would definitely be a red flag. The rest of the information, however, is important. So, in other words, they got this deep sea station. Apparently, it's 200 meters below the surface of the Pacific Ocean. You probably know that as you dive in the ocean, the further you go down, the more pressure you have. So this is saying how many liters of gas at STP. Listen, the initial conditions of this gas is STP. And you remember that STP is equivalent to 0 degrees Celsius and 1 atmosphere. Okay, that's STP. So that's probably going to become an important piece of information, but that's the initial condition. How many liters of gas at 0 degrees Celsius and 1 atmosphere must be compressed on the surface in order to fill the entire underground environment, okay, with 2.0 times 10 to the 7th liters of that gas. And now you see the effect of pressure. If I go apparently 100 meters deep into the Pacific Ocean, I'm increasing my pressure to about 20 atmospheres. And then, of course, the other important piece of information, something that we don't want to eliminate here, is it says, assume that the temperature remains constant. Now, I told you to look out for things like that because they're important. And it's important in this regard. It's telling us the temperature is not important. Okay, so we're going to use Boyle's Law. And the reason why we're going to use Boyle's Law, okay, that was a mistake, okay. The reason why we're going to use Boyle's Law is, there we go, we're comparing initial conditions of pressure and volume to final conditions of pressure and volume. We're trying to figure out how many initial liters. So we're not solving for V2, we're actually solving for V1. A little bit different, but, you know, so be it. Okay, when I do that, when I put in the initial conditions, okay, now remember, the initial conditions, initially my pressure is at STP, which is defined as 1 atmosphere. Okay, my initial volume is what I'm trying to solve for. How many liters of this stuff this gas do I have to compress in order for it to fill an entire compartment, okay? So I use my STP over here, has nothing to do with my initial temperature, but I'm going to use it definitely for my initial pressure. Okay, so it's important that you get to know that. Once you put it in, our final conditions, as you can see, is 20 atmospheres and 2.00 times 10 to the 7th liters. So I'm looking for the volume, the initial volume of the gas that needs to be compressed to fill those requirements in this deep sea thing. When I do that, solving for V1, okay, using algebra, which you should know, and being able to multiply numbers in scientific notation, I get 4.0 times 10 to the 8th liters. Okay? So, that's how we do number 66 here. That's the correct answer there. Okay? But let's look at now numbers 68 and 69 real quick. Just, actually 68 first. So, number 68, let's read it. A container holds 265 milliliters of chlorine gas, Cl2. If the gas is at STP, what is its mass? Now, this is important. If the gas is at STP, whenever you have a gas at STP, the little red flag should go up, okay? That red flag is that any gas at STP is going, 1 mole of any gas at STP occupies 22.4. But because I'm given 265 milliliters of the gas, I can figure out how many moles are contained in 265 milliliters of that gas because the gas is at STP. If this gas were at any other combination of pressure and temperature, I wouldn't be able to solve this problem. Because it's at STP, and I know in the back of my mind, because I study well, I know that any gas at STP occupies 22.4 liters. I'm going to knock this one out of the park. The first thing I need to do is take milliliters, 265 millimeters, and convert it into liters by dividing by 1,000. 265 milliliters times the fact that I'll cancel out milliliters, leave you with liters. I essentially divide 265 by 1,000 to get 0.265 liters. So this is the volume of the gas, remember, at STP. Okay, so that's the volume at STP. Now, again, in the back of your mind, you should know that STP, 1 mole of any gas, occupies 22.4 liters. Now let's sit and pause and think about that for a second. At STP, which happens to be 0 degrees Celsius and 1 mole, or 1 atmosphere, excuse me, I know that 1 mole of any and every and all gas, I don't care what gas it is, how heavy, how massive, I don't care. At STP, 1 mole of it will occupy 22.4 liters. So an entire mole of this stuff occupies 22.4 liters. We just converted and figured that out, that at STP, this chlorine gas sample only occupies 0.265 liters. So the question becomes, is that less than, equal to, or more than a mole? Well, if 1 mole at STP occupies 22.4 liters, and this particular chlorine sample only occupies 0.265 liters at STP, we know that this chlorine sample is going to be less than 1 mole. Of course, we can, using our newest and greatest conversion factor, convert 0.265 milliliters into, 0.265 liters into moles using this nifty conversion factor that Chapter 11 introduced us to. 1 mole is equivalent to 22.4 liters. Doing so, I get 0.01183 moles of chlorine gas. And I highlighted the Cl2 here because it's going to be important, right? This problem's ultimately asking, what is the mass of the gas? Well, if I don't know what gas I have, no way I can convert from number of moles into mass if I don't know the identity of the gas. But because I know the identity of the gas and I've done chemistry and mastered the previous chapters, I know that I can use the periodic table, taking chlorine, the molar mass of chlorine given there, 35.45, and doubling it. I can figure out that because I'm doubling it, because it's not just chlorine gas alone, it is Cl2, as you can see by the subscript there, okay? I take the molar mass given, okay, and I ultimately end up taking the number of moles which I found from the problem of 0.01183 multiplying that times the factor, cancel out moles and leave me with grams. And I know the periodic table tells me that 1 mole of chlorine gas, CO2, occupies 70.1 grams. Therefore, 70.1 times 0.01183 is going to give me my answer of 0.8293 grams of chlorine gas. So this particular sample of chlorine gas that is contained in 265 milliliters at STP actually has a mass of 0.8293 grams. So that's number 68. Let's look at number 69. Number 69 reads, okay, suppose that 3.11 moles of carbon dioxide is at a pressure of 0.820 atmospheres and a temperature of 39 degrees Celsius. What is the volume of the sample in liters? Okay, this is the first of our PV equals nRT problems. And the reason why I know that, okay, the most difficult part of these problems is just determining which of the 5 or 6 available equations that I'm going to use. This problem's telling me that I need moles. The only one of my equations that actually has a factor for moles is my ideal gas law. Okay, so my given information is number of moles is 3.11 moles. My pressure initially is 0.820 atmospheres. And I'm given an initial temperature of 39 degrees Celsius, which is bunk, because I can't use degrees Celsius first. I have to convert to Kelvin by adding the degree given, 39 degrees Celsius, to 273 to come away with 312. So those are my initial conditions. Okay, I'm looking for my volume. Okay, again, I use PV equals nRT. Now, what am I solving for? I'm solving for volume, so I can just algebraically divide both sides by P to get V by itself. That's what I'm looking to solve. So I actually use a variation of the equation, solving for volume equals the number of moles times the ideal gas constant, which will be provided, times the temperature divided by the pressure. So I essentially plug everything in. 3.11 moles times 0.0821 times 312 Kelvin divided by 0.820 atmosphere. You say, why do I use this particular, where did I get it? This value of the ideal gas constant. I use that value because I'm working with the pressure in atmospheres, which I told you on the test. For these problems, I always keep the pressure in atmospheres. Therefore, you can always use this ideal gas constant, which also will be provided. I do all that math, and I come away with a volume of 97.15 liters. Okay? So there you have number 66 through 69, skipping 67 and 70. All right? Peace out.